Hi, my name is Mike Cecina. I'm one of the product managers at MathWorks focused on the automotive products. I'm joined today by Shankar Abanov, one of our application engineers who focuses on real-time applications and hardware-in-the-loop testing. What we're going to show you today is an application of a real-time driver-in-the-loop simulator. So as you can see here, Abi is driving around using the steering wheel and a gas and brake pedal that he has below him to drive around this virtual version of M-City, which is a test grounds. So we're going to talk today about what are the pieces we use to put this demo together and walk you through some of those steps. So why would you do one of these kinds of tests to begin? Now, this is one way, for example, you could author different test scenarios, just drive around yourself and say, okay, here are the interesting scenes that I'd like to do, the different maneuvers that I'd like to capture, and maybe generate synthetic data for later playback testing and post-processing. Sometimes it's just difficult to find time on those test vehicles, so this is another way to obtain some of those tests and drive vehicles in a safe environment. Now, this is just the foundation of how these pieces come together. You could, of course, extend this into autonomous driving applications. For example, maybe you would become the reference driver for some kind of training on the autonomous driving behavior, or maybe the human lead driver for some kind of autonomous platooning application where you want to see if the automated driving vehicles will follow the lead car appropriately. Or maybe to test the handoff between driver and autonomous control. So these are a variety of applications that our customers are looking at. So what are the pieces we use to put this together? First, we had the driver control hardware that you see here. Now ours, we had a steering wheel as well as a brake pedal and gas pedal. Now there's the SpeedGoat real-time target machine we used for the real-time aspect of this real-time simulator. And then we have the Unreal Engine that we used for the visualization that you were seeing in the beginning. And we'll talk about how these pieces all come together using the vehicle dynamics block set and the Simulink real-time. Now, I'm going to start by explaining more of the vehicle dynamics block set, what that product is and what it's intended to do, and then I'll turn it over to Abi to talk more about Simulink real-time. So to begin, the vehicle dynamics block set came about as a request from customers that we'd heard that were working in vehicle dynamics applications. They were testing things about rollover, stopping distance, stability controls, and typically they were answering these questions with combinations of prototypes and simulations. Now, obviously prototypes are expensive, so they're trying to use simulation as much as possible, but often those simulation tools can be quite expensive and kind of geared more towards vehicle dynamics experts. What they really wanted was some kind of a way to integrate their Simulink controls with a vehicle dynamics plant model in a seamless way. And so with that, we introduced the vehicle dynamics block set in our 2018A. So this is a way that that our customers can use the vehicle dynamics models to do things like ride and handling, where they can assess kind of the lateral acceleration of the vehicle as it goes through different test maneuvers. They can do chassis controls design work. Maybe they want to look to see what is the braking performance of a system and how does it handle with the stability controls. Or maybe they want to do some kind of ADAS or automated driving application where they want to have a virtual 3D environment for testing those features. Now, Vehicle Dynamics block set comes with three main features. It has a library of blocks, an integration to game engine, and these pre-built reference applications where we put everything together for you in these fully assembled models. So looking at those, the library of blocks that you see here, these are the way that we've decomposed the block library for Vehicle Dynamics. It has some simple powertrain models. If you want to get more in-depth in the powertrain, there is powertrain block set for that. It has tire models for the longitudinal and lateral slip behavior. We have a variety of different steering configurations and suspension configurations depending on what your application is. And we have vehicle bodies from the simple bicycle model up to a full 6-degree of freedom chassis model. And then we have the vehicle scenarios where you would put in the driver and the different test scenarios, including the Unreal Engine. So what we're doing here is Simulink is actually co-simulating with the Unreal Engine from Epic Games. We're using Simulink to determine all the physics on the vehicle, the forces, the moments, and send that information about the vehicle down to the Unreal Engine where we do the rendering and the lighting. Now, the Unreal Engine is doing its own physics calculations as well. So it's looking for things like collision detection with objects. And if it sees those, it will move those objects accordingly with its own physics calculations. Now you can close the loop with Unreal Engine, so we are actually sending information back to Simulink, things like the ground height underneath the tires, as well as images, because we have kind of an ideal camera sensor in the front of this vehicle that can send back RGB data into Simulink, so you could do some kind of vision-based testing. Now we have the block library, we have the connection to the Unreal Engine. We put these together into reference applications. So there's a variety of those depending on what you're trying to do. If you're looking at vehicle maneuvers where you want to analyze the ride and handling, then we have a variety of different test procedures you can run with those, such as the double lane change you saw in the beginning. But of course, you could customize that for your particular needs. We also have a scene interrogation reference application that's more focused on the connection to the game engine if you want to look more in depth at that particular aspect of the tools. And lastly, we've introduced a kinematics and compliance, or KNC, test lab, where you can perform some kind of testing on a multi-body suspension tool and then import that data into a mapped suspension model to allow you to have some kind of hill-based testing. So let's take a closer look at the reference applications for the vehicle maneuvers. That's what we used as the baseline for the tests in the driving simulator. So here you're looking at the double lane change maneuver. I'm going to walk you through the different subsystems, give you just a real high level overview as to what is inside of them. And then Abhi will later kind of talk about what modifications we made to take it from the pre-built reference application into the driving simulator. So first up on the top left, we have the reference maneuver. So this block here is what's used to define the target velocity. In other words, how fast should the car be going and how far left and right of center should it be moving over time. So the double lane change defines those waypoints for the driver to follow. And then next up, you have the driver that says, okay, given that reference, what steering command and what gas and brake command should I send in order to meet those trajectories? There's different ways that you can have the driver follow those, either with a PI control or maybe some kind of predictive control where you have a simplified kind of MPC approach that you're looking ahead and defining what are the ideal or optimal control inputs to meet that target. Next up is the environment block. This is where you define the prevailing wind conditions as well as some ground feedback. So you can specify the ground as just being an open loop command, just a time or even a constant value for the ground value. You can also use the game engine to provide that feedback directly to the tire. So you can say, okay, here is the height underneath each of those tires as I move through the game engine, and then you can get that feedback accordingly. Next up is the controllers. So in this section, you can see that we have some different controllers for the engine, the transmission, the brakes, and the active differential. Now we provided some basic controllers for you here, like you can see the upshift, downshift strategy for the transmission controller, but this is all based on Simulink. So if you want to put your own controllers in here, this is intended as a starting point for you to customize and really put in your own controllers or your own plant models as necessary. For the plant models here, this subsystem is where we have several areas to look at. We have the engine, or if you want, you can bring in electric motor and batteries. And then that's providing torque down to the transmission, the driveline. Those are connected to the steering. The steering then connects down to the suspension, and you have the vehicle body and the tire ultimately transmitting the forces down. So you can again select different variants. We have different kind of models that you might want to choose from for each of those subsystems, or you could customize them further, put in your own parameters, put in your own subsystems, and really kind of tailor it to your particular application. Lastly, we have the visualization. Here's where we house things like different scopes and gauges and logs, as well as the connection to the 3D engine. So when all that comes together, then you can start running these kinds of tests. So this is an example of a double lane change running at 30 miles per hour. So as the vehicle starts, we're getting some kind of a torque from the engine that brings the torque all the way through the driveline down to the wheels. And then the driver is told to kind of steer left and then steer back right again in order to go through those cones. And then we bring it to a stop at the end. Now, kind of for fun, we hit some of the barrels there. But the point is that this is one application you can use for a double lane change. Then you could go further. You could test it with different parametric variations. So here we have the same driver, the same vehicle, but we're going to run it now at 50 miles per hour. So with this kind of a speed, the vehicle does not make those turns. So you can see the collision detection happening now. So you can kind of see when the playback happens that once that vehicle comes in contact with the cones, the Unreal Engine detects that, sends the cones flying. And similarly, as you get to the end here, you can see kind of the lateral slip as the car kind of comes to a halt at the end of that test. So in summary here, the vehicle dynamics block set, it's providing you this library of components that are open and customizable for those subsystems. So you can really take the subsystems that we give you as a starting point and then create your own particular variants from that. They're fast running, so these are really intended for hill deployment, as you'll see with the next part of the presentation. And Abhi will talk about how he connected this with the Unreal Engine using Simulink real-time and the other pieces that we'll show you in a minute. So with that, I'll turn it over to Abhi.
Thank you, Mike, for that overview of Vehicle Dynamics block set. Now, let us take a look at Simulink Real-Time that will allow us to take our Vehicle Dynamics model and run it in real time. Simulink Real-Time allows you to extend beyond desktop simulation by running models at the required speeds and respecting precise timing requirements and providing interfaces to connect to your hardware under test. Simulink models run on the SpeedGo target computer, which is running the Simulink real-time kernel, which allows you to achieve real-time performance. I'd like to give you some more information about the target computer. It is made by a hardware associate company called SpeedGo. SpeedGo creates target computers in a variety of form factors with support for various I/O modules. Simulink Real-Time and SpeedGo Target Computer are expressly designed to work with each other. Simulink Real-Time and SpeedGo together are the official MathWorks real-time solution. What we are essentially trying to do here is hardware in the loop. I'd like to give you a brief overview of what that means. Consider a system model with controller and plant. What we are going to do in Simulink is remove the controller model and replace it with I/O interface blocks in order to connect with the controller. Then we generate a real-time application that runs on the SpeedGo target computer and connects with the external hardware. Now let's take a look at how we can transform the vehicle dynamics model that Mike presented into a driver in the loop simulator. Mike showed a double lane change vehicle dynamics model, but for our driver in the loop simulator application, we will not need the maneuver or the predictive driver that Mike showed. So let's cut those part out. What we would need is an interface to an external driver. So let's add that part. This interface to the external driver would actually be a Logitech G29 steering wheel interface, which will allow us to drive the vehicle around. Now this interface block allows you to directly connect a Logitech G29 steering wheel to the SpeedGo target computer. It gives you access to the steering inputs, pedal inputs, and the various other buttons as well. Now let's take the steering input for example. It is received as an unsigned integer varying from 0 to 65535, ranging from the leftmost position to the rightmost position. Now once that value is received, we will have to filter out, remove spikes and hardware transients, and then convert them to engineering units. For example, the steering value will have to be converted into an angular representation from a position value. The throttle, brake, and clutch pedal inputs are transformed into a value ranging from 0 to 1. 0 when the pedals are not pressed, 1 when the pedals are fully pressed. Now we want to test the driver in the loop model in real time, so we will have to separate out the vehicle dynamics model and the visualization piece.